My memory is that yesterday we stopped at this point. Fourier transforms of several variables. I don't know why this wasn't highlighted as an important thing to know about. So I'll do that now. Of course, what you do is you just repeat what you already learned for the case of one Fourier transform. You just do it for two, and you can then go for n Fourier transforms. You just put 2 pi to the n over 2, and then the inverse is it looks like this, with again 2 pi to the n over 2. All the integrals run from minus infinity to plus infinity. And you can also relate the Fourier transform variables to the Fourier transform coefficient. So in other words, the function f of x can be written as a Fourier series in terms of the Fourier transform variables at discrete points, namely kj 2 pi j over L. And but it can also be written in terms of the again directly in terms of the Fourier coefficients in that way. Well, no, that's just an example for n equals 3. So in other words, this is the Fourier transform function, but evaluated at these discrete points. I think I mentioned this example last time. What I perhaps forgot to emphasize to you is that a coherent state these are in the notes on chapter 1. Alpha is an eigenstate of an annihilation operator with a complex eigenvalue. And so the reason why this thing works here is that e to the minus c star a on alpha is just e to the minus c star alpha. And if you take the adjoint of this relation, you get alpha a adjoint is equal to alpha star. Of course, alpha star is just a number, so you can write this also as alpha star bra alpha. And that means then that here alpha e to the c a dagger is alpha e to the c alpha star. And that's how this comes about. I thought I'd also sneak in something, a related characteristic function. Some density operators possess p representations. That is, they can be written as outer products of coherent states. This is not true for all density operators, but for a large class, you can write them this way. So then if you take this expression for, wow, this is supposed to be the normally ordered. Let me fix this. It's supposed to be an n there. So the normally ordered characteristic function is one in which the operators, remember the trace is cyclic. So what you actually have there, let me switch maybe to blue, is you have the normally ordered characteristic function is the trace, and if you want, you can write that as rho e to the c a dagger. Hold on, let me fix that. E to the minus c star A. And now if you remember that the trace is cyclic, and so you can write this as the trace of e to the minus c star A, that's an E, rho e to the c A dagger. And now if you write rho in terms of outer products of coherent states, you see that this turns into this integral here. This coherent state is an eigenstate of A, alpha is an eigenstate of A dagger, and so you get just this expression. And this is a complex, this thing is linear in the real and imaginary parts of alpha, and it's purely imaginary. And consequently, this is a Fourier transform of the function P of alpha. And that leads us to why it is that the P representation doesn't exist everywhere. And the reason is that it has to be a Fourier transform of the normally ordered characteristic function. And the normally ordered characteristic function does not always have Fourier transforms. On the other hand, the anti-normally ordered characteristic function does. And its Fourier transform is this very, very smooth function, which is just the diagonal matrix elements of the density operator in a coherent state. And remember that I said to you that Fourier transformation maps sharp into smooth and smooth into sharp. So this is smooth. So the anti-normally ordered characteristic function must be kind of sharp. On the other hand, the normally ordered one must be kind of smooth. And then P of alpha is sometimes too sharp to be a function. In fact, too sharp even to be a distribution of any ordinary kind. One can derive the Helmholtz decomposition algebraically by using the Levi-Civita formula in terms of Fourier and Fourier transforms. So you first write V of k. That V is just any vector. You can write any vector in this form, any three vector in this form, k dot V times k over k squared, and then k cross V over k squared. And the magnitude of k cancels here. And on the other hand, k is minus I gradient, and the same thing over here. And so what you wind up with is the gradient of the integral of minus I k dot V over k squared, Fourier transformed, and then the curl of the Fourier transform of I k cross V over k squared. So this is, we've expressed any vector function as the sum of the gradient of a scalar plus the curl of a vector. And that's the Helmholtz decomposition, but derived algebraically in terms of Fourier transforms rather than the more direct but more difficult way that we did it in chapter 2. As I said to you yesterday, Fourier transforms are just amazingly useful in physics, especially theoretical physics, but in fact, in all kinds of applications of physics. If you have a spinless quantum field of mass m, such as, for example, one component of the Higgs field, then there's something that Feynman introduced, the appropriate propagator that Feynman introduced is this Fourier transform. So you see it is a Fourier transform. Here, though, k dot x it's a four-dimensional Fourier transform. K dot x is the Lorentz inner product of k and x. Let me see if I can get rid of this because it's blocking part of the screen. Now, here I'm using what are called natural units, which are explained in, well, I'll have to post that chapter where I explain natural units. I'll post it on the class website. If I remember, I'll post it tonight. Anyway, natural units are where you set C and H bar equal to 1. Setting C equal to 1 means you are measuring distance as light seconds. And so then you've got time, and then you measure time as inverse second, energy as inverse seconds, setting H bar equal to 1. And so what we have then is this expression here. And it turns out, as we'll see in chapter 6, that this Feynman propagator can be written as the average value in the vacuum of the product of the fields when they're written in time order, and the product of the fields in anti-time order, added together. And this, of course, is this Heaviside step function, which that used to make me chuckle every time I saw it, but I've seen it now so many times that I'm afraid the chuckle is worn off. So we'll get to more examples later in this chapter of the applicability of Fourier transforms in physics. But in fact, here another example is simply this: the convolution. The convolution of a function f of x with a function g of x is a certain integral. And that doesn't look as though it has anything to do with Fourier transforms. It's an integral dy over root 2 pi. And it's f of x minus y times g of y. And it turns out it's like any good, well, it's symmetric. F of f times g is equal to g times f. And the way to see that is you can write f times g. Well, this is the definition of the convolution. Now you set z equal to x minus y, and then y is x minus z. So we have this. But now dy is minus dz, and dz goes from or the y integration was from minus infinity to plus infinity. It goes from plus infinity to minus infinity dz. And that flips over to minus infinity to plus infinity dz, g of x minus z, f of z. And that's the convolution of g with f. So it's symmetric, which makes it more useful. And in physics, they often occur in this form, namely that some physical observable is due to a source, and the relation between the two is an integral like this of x minus x prime. And you've seen many examples of this in electrodynamics. I suppose there may be examples in quantum mechanics, but they don't come to mind immediately. I think since we're going to go more slowly in chapter 4, I'll go through this example, which is, of course, really important. One of the peculiar things about nature is that it's described by theories with an extraordinary amount of symmetry. I think Einstein and others realized that the reason for that, the deep reason for that, is that nature doesn't know what coordinate system or what variables we're going to focus on. And so if the true equations of nature are to make any sense, they must make sense independent of human conventions. And that means that they have to be very, very symmetrical. And general relativity, in fact, the basic principle of general relativity is that it's the simplest possible theory of gravity in which the equations remain invariant under general coordinate transformations of the four space-time variables. And that's basically it. That tells you what general relativity is and completely defines the theory. In the ordinary thought of physics that we deal with in electrodynamics and in particle physics, equivalently in the standard model of particle physics, which I like to call the standard muddle of particle physics, the symmetries are called gauge symmetries, and what is meant is one can make local transformations of specific kinds. So it's much more restricted than the symmetry of general relativity. I once wrote a paper about generalizing it, and as far as I know, it's gone unnoticed for 50 years. Well, anyway, let's continue with this. One property of these theories, by the way, of the standard model, these are called gauge theories, and the symmetry is called gauge invariance. And what is meant is that the symmetry is local, and one consequence of local symmetry is that there are constraints. And the constraint in the case of electrodynamics is Gauss's law. Notice that this is an equation that tells you that something on the left-hand side at time t is related to something on the right-hand side at the same time t. And there are no time derivatives which say you have to get the left-hand side, you have to integrate in time. So this is called Gauss's law, and it's something that doesn't occur in ordinary classical mechanics unless you're dealing with the constraint of, for example, this thing is constrained to be on the edge of the table until I move it to the edge, and then it falls. So constraints like that in mechanics are examples of constraints, but since we no longer teach mechanics due to the stupidity of some of my colleagues, you won't learn about constraints in mechanics, at least not in an ordinary course in this department. Anyway, this is Gauss's law, and the electric field in the Helmholtz decomposition, if you drop the curl part, you just get that the electric field is the gradient of something. And we conventionally put in a minus sign, and so Gauss's law turns into divergence of E is minus the divergence of the gradient of the scalar potential. That's minus the Laplacian of the scalar potential, and that's the charge density over the electric constant, the electric permittivity, I should say. And although I like to use natural units and sometimes slip into them, I've tried in most equations in this book to use just ordinary MKS units, so that things are, well, I mean, in a certain, well, so that these equations are more accessible and more applicable, widely applicable. So we can solve this equation by using Fourier transforms. What we first of all do is we write phi as its Fourier transform. Then we take the gradient in there, and the gradient on, let me just write that explicitly, the gradient with respect to x on e to the I k dot x Well, that's equal to ik dot whatever there is here, e to the I k dot x. And so what, so you get a, and if you do it twice, you get a k squared. So gradient squared e to the I k dot x is equal to minus k squared e to the I k dot x. And let me maybe switch colors so that we, whoops. So maybe I'll switch to red. Okay. And so that gets us to here. On the other hand, Gauss's law says that's rho of x over the electric permittivity, and consequently, then we write rho in terms of its Fourier transform, which we call rho tilde. Now, you might say this is 2 steps backwards, but it gives us an algebraic equation, namely that phi tilde is equal to rho tilde over epsilon 0 k squared, or the k squared phi tilde is equal to rho tilde over epsilon 0. And that means then that we can write phi in terms of a known, its known Fourier transform, which is rho tilde over epsilon 0 k squared. And now, one thing we can do with that is write rho of k in terms of the density at a different point. And then if we gather everything together, we get it in the form of a convolution where the convoluting function is called a Green function or Green's function. Green's meaning invented by Green, or one of Green's functions, having nothing to do with the color green, except that Green's last name was the color green. Anyway, g of x minus x prime then from this equation, what is it? Well, it's what's left here. In other words, when we express this, when we rewrite this formula in terms of g, the way we've done that is we've taken the 1 over k squared and the Fourier transform e to the I k dot x minus x prime, and we've used that to make g of x minus x prime. And what turns out is that g of x minus x prime is the Green's function for the differential operator minus Laplacian. And so what Green realized was that you could solve a lot of differential equations efficiently if you invented functions that were inverses of the differential operators. And I don't know quite how he thought of the thing as in modern terms, post-Dirac terms, this Green's function is defined by minus Laplacian on the Green's function gives you the delta function. But when Green was writing, he had to sort of see this in a different form, which of course made it harder for him to do that, but he was quite smart and worked that out. Schwinger, by the way, used Green's, got so much mileage out of Green's functions that on a trip to Europe, he visited Green's birthplace. So we can think of the Green's function as the inverse of a differential operator. In this case, g is the inverse of minus Laplacian. And to compute what it is, well, it's given by this expression here. And you can see that let's see, did I say why it's obvious that this works? Maybe I should say why it's obvious that this works. So let us do minus Laplacian on G of x minus x prime using this equation here. Well, this would be an integral e cubed k over 2 pi cubed. And minus Laplacian there would just bring down k squared, which would cancel the k squared here. And you just have e to the I k dot x minus x prime. These being vectors. The k squareds cancel, and what's left is delta cubed of x minus x prime. Okay, I don't quite know why these, well, never mind that. Anyway, so that's why this is the Green's function. And to compute it, well, we use the formula, we go to spherical coordinates, and the phi integration is immediate. It just gives us 2 pi. The cosine, we can write k dot x in terms of a cosine of an angle between, let us say, the z-axis and the vector x minus x prime. We do the cosine integral, we get this. Now we rewrite this as a sine, and we bring the x minus x prime outside, and we wind up with this. Now, this, of course, is just a number. The particular number that it is pi over 2, and we'll see that when we do an application of complex variable theory in chapter 6. So the result then is that the Green's function for minus Laplacian is this integral, and the answer is 1 over 4 pi x minus x prime. Well, this is what you already learned in electrodynamics. Namely, you could write the scalar potential as an integral of the charge density divided by 4 pi, the electric permittivity, and x minus x prime. A similar thing works for the static magnetic vector potential. There, in terms of the permeability of the vacuum mu 0, we have that the curl of B, Maxwell's equations give it the curl of B is the curl of del cross A. That's the gradient of the divergence of A minus Laplacian of A. Now, in the Helmholtz decomposition of the electric of the electric potential, the vector potential A, can write the vector potential as the gradient of something plus, I'm sorry, we can always write the electric field as minus the gradient of something plus the curl of something, and we can choose this to be, we can choose A to have 0 divergence. This is called the Coulomb gauge. The Coulomb gauge condition. And when we do that, we just have minus Laplacian A, and that's then mu 0J. Well, by going through the same procedure that we just went through for the scalar potential, we see what we have is 3 analogs of the scalar potential. Minus Laplacian, the scalar potential equals the charge density over epsilon 0. We have 3 copies of this because because this is a vector equation. And what we find out is that the Fourier transform of the vector potential is the permeability of the vacuum times the current density divided by k squared. And going through the same thing as with we just did with the scalar potential, we find that the vector potential is an integral of the current density divided by the distance times mu 0 over 4 pi. We can notice something here, though. Suppose we change x by a. Well, all we do is we just, the change is quite simple. Let me go back here and change the color. just like to change the color every now. If we change this, all we have is e of x plus a. Of course, I shouldn't have used a since I already have a, but it's too late now. Mu over 4 pi, mu 0 over 4 pi, integral d cubed x prime, and now it's a j of x prime over x plus a minus x prime in absolute value. And if we change x prime, this is effectively, we can let x prime go to x prime plus a, and this is also mu 0 over 4 pi d cubed x prime j of x prime plus a over x minus x prime, if I've done that correctly. And so that's what's nice is that convolutions respect translation invariance. If you change rho to rho plus a, phi goes to phi prime is phi of x plus a. And what I derived it for is that if you change j to, if you change j by adding a, that changes a by a. So convolutions respect translation invariance, and that's why they one of the reasons why they occur and so often in physics. If they didn't, this would be really quite unacceptable. So let's look at the Fourier transform of a convolution. We've defined a convolution like this, and so let's take its Fourier transform. Well, the Fourier transform of the convolution looks like this, and it then is this integral where this is the convolution. And in other words, what we're doing here is writing f star g of, oh, I'm sorry, it actually is k. All right, I'm going to have to as integral minus infinity plus infinity dx over root 2 pi e to the minus I kx integral dy square root of 2 pi f star g. Well, it's actually just f star g of x, and I can use my handy eraser to write it this way. It looks a little silly, but that's what actually one is doing. And so now we replace f star g with this, and oh, that's what I had here. I didn't need to do that. All right, so this is sort of silly what I've done. So let's now do this integration. What we do is we express f and g in terms of their Fourier transforms, g tilde and f tilde, and then Dirac rides to the rescue, and we use the delta function twice, and we just get the product of two Fourier transforms. So the Fourier transform of convolution is the product of the Fourier transforms. So that's that tells us that convolutions are very nice because they not only respect translation invariance, but they also behave simply under Fourier transformation. And it also means that we see that Fourier transforms are even more useful than we thought because they relate so neatly to convolutions. I'm trying to remember when this class ends. I think it's at 6:15. Okay. Fourier transforms and Green's functions. So this is something really quite important And you can see that in that I've colored almost everything in this section, apart from the example. So the Green's function of a differential operator is the inverse of the differential operator in the sense that P times G is delta. And now, in most cases, that gets you nowhere. But when P has a simple form, that it's just a bunch of derivatives, here I said it was a polynomial in derivatives. It actually can be much more general than that. It just as long as P is some function of derivatives, it's quite simple, because P hitting this thing becomes P of ik. Each of the derivatives turns into ik. So it's just P of ik. And on the other hand, we want that to be the nth, the delta function of order n, which is this integral over 2 pi to the n dnk e to the ik dot x. And what does that say? Well, that says that g tilde of k, g tilde sub p of k, is 1 over 2 pi to the n p of ik. And when I wrote that, I was thinking that, well, that's a polynomial with constant coefficients. Actually, it's any function at all. So this is much more general. I'm going to have to change that. It's funny that I should find that out. So generalize 4.8. So that's interesting. So that gives us a formula that the Green's function for any differential operator. Now, the point is the differential operator is independent. See, I said here with constant coefficients. The key thing is that the differential operator should be independent of x. The killer here is that if P depends on x, then it's much more difficult. But if P just depends upon derivatives, it's trivial, and this is the answer. And that, again, is one reason why Fourier transforms are things that people in physics love. An example of their utility is Yukawa's equation, which is minus Laplacian plus m squared on a Green's function, is the delta function. This is really a three-dimensional delta function. And the solution is the Green's function is e to the ik dot x over the Yukawa p of ik, and that's just k squared plus m squared. And now if you do the integration, which we'll do in chapter 6, you get e to the minus mr over r. This is called a Yukawa potential, and it was it is used a great deal in nuclear physics, and it's an approximation to the nuclear forces, which in turn are basically just the long-range part of the QCD forces. And of course, I say that as though I understood or understand what the QCD forces are. Well, I understand in a mathematical sense, but in fact, QCD is a strongly interacting nonlinear gauge theory, and nobody knows how to actually solve the thing analytically to any extent, and perturbation theory doesn't work except at very high energies, where the coupling constant decreases logarithmically as you go up in energy, the effective coupling constant. And so if you go up to high enough energies, you can do perturbation theory. But I think not even the SSC would have gotten us to high enough energies. Let me just switch here to make sure we've got it. All right. So Laplace transforms, I can at least introduce them in the time remaining. They're like a Fourier transform, but different. In other words, they're an integral So you take a function f, you multiply by e to the minus st, and you integrate just over positive t, and you get the the Laplace transform of f. And what's useful about the Laplace transform is that if f of t is not integrable on the half line, when you multiply it by an exponential, it decreases as you go out in t. Then the integral typically often converges. In fact, just as long as f isn't an exponential, it doesn't grow exponentially, you've got a well-defined Laplace transform. An example is f of t equal to 1. Well, this just integrates to 1 over s. E to the kt diverges, but if you pick s greater than k, you have a Laplace transform that's well defined for s greater than k. So this gives you a definition of the Laplace transform, and because of the way s appears here, you can say, well, this works if s is bigger than such and such, and in this case it's k. The cosh, sinh, cos, and sine are all four of them are linear combinations of exponentials, and so you can, using this, you can compute their Laplace transforms, and they all go as essentially 1 over s, like this, and they all have something going on either at I omega or minus I omega or ik or minus ik. The Laplace transform of t to a complex power is related to the gamma function. Well, the lifetime of a fluorophore, those of you interested in biophysics might want to study that, but I don't think we need to go through it. The inversion of a Laplace transform, well, you can invert them, and the way you do that is you use, once again, Dirac's delta function. So how do you do that? Well, you first of all notice that you extend it to a complex argument, and then what you do is you integrate over that imaginary part du, and you do it at a value of s that's sufficiently far out that this is going to converge. And when you do that integral, if you imagine that you know what the Laplace transform or the inverse Laplace transform is, and just substitute it, write it abstractly as f of t prime, you then see that the du integration gives us just delta of t minus t prime. So you get that this integral over the imaginary part of the argument of the Laplace transform is actually the function you started with, or the function you're looking for, times e to the minus st. So the inversion formula is that the inverse Laplace transform of f is this integral where you're integrating du at a value of s. In other words, s is sitting here in two places, and you choose s sufficiently large that this integral converges. And this is called a Bromwich or a Fourier-Mellin integral. All right, we seem to be out of time. I don't see any chat questions. Does somebody want to type in a chat question? Or what I think I'm going to do is I'm going to stop recording now.